Hi, welcome to today's session, EKS-Workshop, Implementing Serverless Scalable Kubernetes in the Cloud, with Spot Solutions Architect Team Lead Amit Bar-Oz.
Hello, everyone. My name is Amit. I'm leading the Solutions Architect team here at Spot by NetApp. And today we're going to talk about how to implement a serverless scalable Kubernetes solution on the cloud using our product name Ocean. So it's a pleasure to be here, and let's begin. We'll start with the anatomy of Kubernetes. Essentially, Kubernetes is a solution that is here in order to allow you to run containers at scale. There is two main components while talking about a Kubernetes cluster. We have the control plane and we have the data plane. So essentially, the control plane is responsible of making sure all the containers that you're running are able to properly run on top of the data plane that is associated with the cluster. So essentially, the nodes that are attached to the cluster itself. Each one of the nodes of the data plane will have a service that is called kubelet, or in other words, the node agent that will be the way for the control plane to communicate with the nodes themselves. In addition to that, we have a utility that is called services that they are meant in order to allow us to expose our containers, our services that we're running to the outside world and of course inside the cluster itself. But these are the things that allow us to add the communication layer for our pods, which are the smallest entity that you can define in a Kubernetes cluster. Essentially, a pod will be one container or more attached to a certain service. While talking about scaling in Kubernetes, we have two different layers of scaling. We have the infrastructure layer and the pods layer. So essentially, you will be able to add more and more containers that you want to be running on the cluster. And essentially what we will need is to have instances behind the scenes that will be able to run those containers. And this is the infrastructure side of things. So we always need to take care of both of them. While talking about scaling for the infrastructure side, the way to do it by yourself or using the open source tools, there is a tool that is called Cluster Autoscaler. Essentially, what it does, it increases and decreases the size of the cluster when you have pods that cannot be scheduled due to lack of resources, meaning they are in a pending state, and it will decrease the cluster size when nodes will be underutilized. So essentially, we'll have pods in pending states. The cluster autoscaler will recognize that. It will launch a new node, and then the pod will be able to be scheduled there. While talking about the pod level, we have two different types of autoscaling. We have the horizontal pod autoscaler and the vertical pod autoscaler. Both of them are checking a utility that is called deployment, and based on the metric server that you will have installed with the cluster, on the cluster they will be able to monitor the actual consumption of the pods that you currently have, and based on that, it will set the HPA will set the amount of required pods, the amount of replicas for this specific deployment. While the vertical pod autoscaler, what it will do, it will actually recognize that there are more resources needed, and therefore it will increase the sizing of the pods themselves. Meaning we will take one pod that has certain requests, it will increase it, and then the pod will be restarted, meaning it will have to start again. Now, the problem with Kubernetes on the cloud is that we want to do two things. We want to make sure that we're meeting the application demands on one hand, and from the other hand, we want to minimize idle resources as much as possible. And this is crucial because essentially running resources on top of the cloud is very, very expensive. So we want to be as efficient as possible. And actually what we can do behind the scenes in order to allow that or play with those things is to define different instance sizing for our clusters, to work with different life cycles of machines. So we can use on-demand machines, we can use reservations, and we can also use cloud excess capacity, which in AWS is called spot instances. And there is another layer, which is the pod right sizing. So we want our pods to require the resources that they're actually utilizing behind the scenes in order to make sure that we don't have any waste of resources. So these are the three main things that we as the people who manage the infrastructure are able to play with in order to make sure that we're actually solving this specific problem that we have. I want to talk about a different approach for autoscaling. We want to talk about container-driven scaling. We want to stop thinking about the nodes, the infrastructure. We want to focus on our containers. And essentially, we want to look at containers as our first citizen. We want to see each one of the pods, what's the requirements, the types, the pricing of the instances that are actually needed in order to run those pods and containers, in order to make sure that we honor their requests and the constraints that are specified with those. And based on the container needs to launch the correct infrastructure in order for it to be able to be scheduled. And this is the approach that we want to get to. And essentially, what Ocean does is it's a Kubernetes data plane management, meaning we can hook up to pretty much any different control plane that manages containers. It could be ECS, it could be any Kubernetes deployment on top of AWS, it could be GKE and AKS and even OpenShift. And essentially, we will be able to hook up to this containers control plane, to this container orchestration platform, and we will be able to associate the best infrastructure in order to suit the application's needs. Let's talk a little bit about achieving a serverless or nodeless experience and what it means. So what we want to achieve is the ability to not needing to manage the underlying infrastructure. We want our infrastructure to scale by request based on the real-time requirements of our containers. We want to only pay for what we use. We want to eliminate any waste that is associated with the cluster. We want to have the ability to scale down all the way to 0. And we want to scale fast. We don't want our containers to wait while instances are being launched. We want to satisfy our container needs immediately. And let's talk a little bit about numbers. So in this specific example, we have a pod that requires 6.5 gigabytes of memory and 1.5 vCPUs. And essentially, we're talking now on different instance sizes. So if we're talking about the instance type that will satisfy the need for this container, it will be probably an M5 large. Essentially, the pod will utilize 81% of their memory and 75% of the CPU. This would be the price per pod. Now, once our pods are being scaled up and we have more pods from the same deployment, we can see that we could use more M5 large machines, but we can also use bigger machines. So in some verticals, it doesn't really matter. But if, for example, our deployment is going to have 5 replicas, we will be able to utilize a bigger machine type with smaller costs just because the pods could still utilize resources that are available in the cluster. So essentially, what we can see here is that by going a few sizes up, we can actually achieve better resource allocation and reduce the cluster cost by about 20% in this specific example. So the ability to actually look at all of the pods that are running in the cluster as a whole will allow us to, in this case, have much better utilization and allocation of the resources. So let's talk about a little things that Ocean adds on top of it. So Ocean essentially is a serverless container solution. It allows you to deploy containers on an abstracted infrastructure with the ability to save up to 90% on your costs. And we do that by providing a container-driven auto-scaling solution. So we will auto-detect the pod or the task's infrastructure that is required. And based on that, we will launch the appropriate instance size, type, and lifecycle, and make sure that you constantly have the infrastructure available for your needs. And the second thing is that we will simplify your operations. So essentially, we will be able to utilize multiple different machine types, different sizes, and different availability zones, and even life cycles based on the actual requirements of your containers, and allow you to focus on your application rather than needing to deal with the infrastructure. And I'll show an example to that quite soon. Few more things that Ocean adds. So we have the cost management and showback. We actually take the pricing of the cluster and we break it down to different namespaces and deployments. And then it allows us to give you a tool that will assist with doing showback and understanding how much cost is associated with each one of the applications or services that you're running on top of the cluster. And we also provide the vertical containers auto-scaling recommendations, which essentially we're able to track the actual utilization of your deployments versus what you requested. And by that, we will track those details for 2 weeks backwards. And we will provide recommendations on how to set your application requests for those to actually utilize the resources. And by that, you can decrease the sizing of the cluster dramatically and therefore eliminate a lot of waste. Another very important thing about our solution is that you can use infrastructure as code in order to use that. So you can create automation around that. So we support tools like Ansible, Terraform, CloudFormation. You can also use our APIs, which are quite extensive, and this will allow you to launch those resources. So now what I'm going to do, I'm going to shift to the demo environment. Essentially what I have an EKS cluster, this one, the EKS-Workshop. And in addition to that, I have an auto-scaling group. This auto-scaling group is currently configured to work with the cluster autoscaler. So we're going to see how the cluster autoscaler operates, and then we're going to jump into Ocean. Now I'm going to jump to my terminal. Here, essentially, you'll see that we have several different files, and if I'll ask to see the deployments that we have, we'll see that we have 3 different deployments on top of this cluster. So we have the large, medium, and small. Now, what's important here is that essentially the differential between those 3 deployments is actually the requests that are specified for each one of them. So the small ones will have a small amount of requests, medium will have bigger requests, and the large will have even bigger requests. Now, the instances that are associated with my autoscaling group are T2 large. So these are quite small. And what we're going to do now is I'm going to scale up the replicas for those specific deployments, and we're going to see how the reaction would be. So we'll start by increasing the small deployment amount to be 3. And what we're going to be able to see now is that this deployment will scale to 3, and we'll also see that the pods are actually running. The reason for that is because the machine was able to actually run those containers. Now, I'm going to do another thing, and this is going to scale the medium deployment that we have. So now, essentially, we're going to have another deployment that you see that it needs to have 3 containers, but in reality, we currently have 0. And if I'm going to run the kget pods, I'm going to see that they're in a pending state. So what I'm expecting to happen now is for the cluster autoscaler to be able to scale up new machines. So let's look at the logs of the cluster autoscaler. Let me just get the new name of the pod. So these are the logs that we can see. What we will be able to see here is that we have pods that are unscheduled. And we can see, okay, so we have 3 pods that are marked as that, and based on that, we will have a scale-up event. So let's see what's happening now. We also already have 1 node that is being attached to the cluster. So if I'll go to the autoscaling group, it used to have 1 machine. Once I'll refresh the page, I'll be able to see that we now have 3 machines that are associated with the cluster. And slowly we will see our pods being scheduled. So we already have 2 pods running out of the 3, and the 3rd one will be running in a short time. Should be running now. sim container created. What I'm going to do now, I'm going to go to my my dashboard of Kubernetes. So let me just fetch the token once again. So now I'm connected to the cluster. And what I want to show you now is if we go to the nodes view, we will be able to see that one of our nodes is actually less utilized. So you can see the two nodes are utilized in 80%, are allocated in 80%, while the last one is 45.5%. Now, essentially, this will trigger a situation where the cluster autoscaler will try to scale down this specific machine. So what I'm going to do now is I'm going to let me decrease the sizing a little bit so it will be more visible. What we'll be able to see now is that the cluster autoscaler actually found the candidate for 42 nodes. Let's give it another go. It's still waiting. But essentially, what will happen with the cluster autoscaler is that it will try to terminate this specific machine. So we will look at it in a second again, but essentially what we have now is we have a cluster that has 3 nodes associated to it. One of the nodes is actually not allocated high enough. And what the cluster autoscaler does behind the scenes is whenever your CPU allocation or memory allocation is below 50%, both metrics are below 50% for a specific instance, it will try to scale it down. But essentially the current situation, if we will scale down this machine, the pod won't have another place to be able to run it. So the machine is actually crucial for the cluster. This is something that we don't want to have within our cluster. We don't want the machine to be lost and then to get the pods to a pending state. This could be quite dangerous for the cluster itself. So this is something that the cluster autoscaler doesn't cover. Now, I want to do another thing in the meanwhile. I want to increase the sizing of the large deployment. Now we're going to see that we have pending pods once again. But in this case, those large pods, the requests are too high for what T2 large can do. So essentially, the cluster autoscaler won't be able to satisfy their needs with any one of the nodes that it's able to launch. So we'll be in a situation where those pods will be stuck at a pending state until we will be able to launch bigger machines that will be able to suit their needs. So what we will see in the log now is that we have pods that have insufficient CPU, and it wouldn't fit a new node that is added to the cluster. So essentially, we're in a situation where our cluster is stuck. And what I want to do in this situation is I want to move to our solution. So what I have here is a spot organization, and essentially this is the Ocean dashboard. What I'm going to do now, I'm going to create a new Ocean cluster from the existing group that I have. So what I'm going to do is I'm going to choose Oregon as the region, and I'm going to find the auto-scaling group that I'm using behind the scenes. So it will be EKS-Workshop, and I'm going to click Next. What we'll see now is that Ocean actually populates all the configurations that are sitting behind the current auto-scaling group. So we'll take the subnet, we'll take the instance profile, the security groups, the image, and so on. So you can see that everything is being configured. By default, Ocean uses all machine types in the cluster. If you'd want to not use a certain machine type, you can just come here and remove it from the selection. And you can even specify from a machine size, the minimum vCPU and maximum vCPU, and same goes for memory per machine. In addition to that, you can configure some additional configurations like the root volume size, the health grace period, and stuff like that. Once I'll click Next, I'll get to the connectivity section. Here, actually, what we have is we need to install a pod that will act as our agent within the cluster. So essentially our controller that allows us to actually understand what's happening in the cluster. In reality, what this pod is doing, it's actually sending all the different resources and metadata of the resources to our SaaS platform. And there we are actually able to understand what's the scaling needs for this specific cluster. So what I'm going to need to do now is to generate a token. I'm going to generate a new token. This will actually be populated in the script. I'll copy this script. I'll go back to my terminal and I'll run the script. We'll actually create some resources on the cluster. So essentially we will see if we have a new pod that is being created. This is our controller. Essentially replaces the cluster autoscaler. Let's wait for it to get to a running state. So now it's getting to a running state. Interesting. And what I want to do now is I want to click the test connectivity button. Okay, so the connectivity is working. I'm going to click next. What you're going to see here is a summarize of the configurations. We can even see it in a JSON view. We can modify some things if needed. And we can even see it generate a Terraform template for this cluster. So technically I can just copy it and create the same cluster through Terraform. For this workshop purposes, I'm just going to click the create button. And what will happen now is our Ocean cluster will be created. It will actually start one machine that will register to the cluster. And a step later, we will scale up according to the pending pods that we currently have in the cluster. We'll see it in a moment. So let's see that our pods are still pending. Okay, so the new node just joined the cluster. Pods are still pending. And we now see that Ocean started to launch new machine in the cluster, new machines. You see that it launched C5 to X large, 2 machines of that type in different zones, and another one of C4 to X large. And these will essentially allow those pods to get to a running state. You see the nodes are already being registered to the cluster. And they are in a container creating state, which is good. Okay, so we already have 2 running pods. The third one is on the way. The node is ready and the pod is probably being created now. So essentially what happened is that since Ocean is able to utilize multiple machine types and different availability zones and even different life cycles, we were able to actually scale up new machines, even though those machines weren't specified specifically. And this was actually based on the needs of the containers themselves. Now, in addition to that, Ocean actually supports the built-in Kubernetes node labels. So if, for example, we will launch a new pod that will require to run on a specific machine type or on a specific availability zone, we will actually be able to scale based on that. So essentially, you can define from your deployment for your pod level, I want this specific pod to run on this specific availability zone or on this specific machine type, or you can use affinity rules to define a list of machine types that is supported for this pod. And in addition to that, we actually support this proprietary node label that will specify that you want a certain pod to run on an on-demand machine. Based on that, Ocean will launch an on-demand machine in order to make sure that we satisfy the pod's need. So essentially, if you have any stateful sets or applications that cannot live on spot instances, you can actually quite easily define this specific pod has to run on on-demand machines. We will take care of it behind the scenes, allowing you to actually define how you want your infrastructure to look like from the pod's perspective, from the application perspective. And this is what we're trying to achieve here. So what I'm going to do now is I'm going to look at an existing cluster in order to have some more details and show you some other benefits of what we actually have with Ocean. So essentially, this is a cluster that is running for quite a while. It was actually created in April 2019. And currently we have 35 nodes that are managed by Ocean. And you can see a tremendous amount of savings, but this is not the main point here. What I want to emphasize on is actually the allocation of the CPU here. So as you can see, we're reaching allocation of around 95+% for this CPU, for the CPU in this cluster. And the reason why we can do that is because we are able to utilize those multiple machine type sizes and availability zones, and even different life cycles. And this is easily defined from the application side of things. So Autoscaler is very aware of what's happening behind the scenes. And if we look at the log section, we will see that for each scaling activity, we actually give the information of what triggered the scaling event. So you can see that in that case, for example, we had before the scale up, we have this amount of CPU and memory. After that, we have that. And you can see the pending deployments and what restrictions they had, what requirements they had, which machine was launched based on that. In addition to that, for scale down activities, you will be able to see the simulation that we run behind the scenes. So Ocean will only scale down a machine once it knows that all the pods that are running on top of this machine are actually able to be scheduled on a different node in the cluster. Otherwise, Ocean will not scale down the machine like the cluster autoscaler does. So essentially, Ocean is aware of the applications that are running and it will not affect the availability of the applications based on that. Now, let's say that we do pack the nodes in a very, very highly manner, but what if we or I don't want to wait for a new instance to launch if I have a new pod coming? I'm using an HBA, I cannot wait for a new instance to launch. So for that exactly, we have a utility that is called Headroom. So essentially, Headroom is a way for you to configure a little bit of extra capacity on top of the cluster. So it can be defined by two different ways. You can either specify manually and say, I want to keep 10 units of X and Y CPU and memory. You can even define GPUs. And Ocean will constantly make sure that you have those units available in the cluster. Another way to define it is actually to use the automatic configuration. There we will define the most frequent used pod size in the cluster. And based on the percentage that you will specify here, we will calculate the units and we'll constantly make sure that those are available in the cluster. So this is very useful if you cannot wait for new instances to launch. This way you can have a little bit of extra capacity on top of the cluster when needed. Another very important thing that we provide here is actually the right sizing recommendations. So in the right sizing recommendations, what we will be able to see is we'll be able to see the entire cluster resources. But in reality, we will see down here all the different deployments that you're running and their recommendations. We will either recommend to downscale the requirements or upscale them depending on what you have currently. And essentially, whenever you will click on a specific deployment, you will be able to see these graphs that actually shows you the actual utilization over time versus the requests versus the limits, both for CPU and memory. And then we look at data of up to 2 weeks backwards, and based on that, we'll give you the actual recommendations of the right sizing. Now, these are just recommendations as of now. We don't automatically apply those, but it is possible to use a third-party Git library that we are able to provide. And then you will be able to define for which one of your deployments you want us to automatically apply the recommendations. And then you will be able to actually utilize that automatically. And this will allow you to not only achieve high allocation of the resources like you can see here, but high utilization as well. Another very important tool that we add is the cost analysis. So here what we do is we actually take the entire pricing of the cluster and we break it down into different namespaces, deployments, stateful sets, and the different resources that you're actually running within your cluster. This actually allows you or help you to differentiate what's the cost for each one of the applications you're running, for each one of the business units that is using this cluster, and you can even group those by different labels and allocations. So it's quite easy in that term. Now, Ocean specifically prefers to utilize any spot instances before launching any on-demand or anything other than that. Now, this could sound a little bit dangerous, but in reality, it's not. The reason for that is because Ocean is able to utilize multiple different spot machine types, and whenever there will be no spot capacity available, we will be able to actually fall back to on-demand and make sure that you have the capacity that you need in order to run your application. Now, as long as your application is stateless and can live with an environment that changes a little bit, Ocean will be able to support that. If it's not, you can always mention you want this specific application or this specific pod to run on an on-demand machine, and we will essentially be able to launch the machine behind the scenes, and then you can run your production workloads, and you should run your production workload with Ocean. Just make sure to specify whenever it's needed that this specific application should not run on spot instances, and you'll be all safe. Essentially, I want to summarize what Ocean does. Essentially, Ocean is a serverless container solution. It's built in order to let you focus on your main business, which is your application, rather than dealing with infrastructure. While you should know that behind the scenes, you have the most optimized infrastructure to suit your container's needs. And you can always define how you want your infrastructure to look like in case of need. So essentially, if you know that there is some constraints or limitation for a specific application, you can always define it from the application side, and Ocean will take care to launch the best and most suitable infrastructure for the application needs. That's from my end. I see that we don't have any questions in the questions tab, so thank you for joining the workshop today. I'll be more than happy if you guys will grab our container solutions brief from the handout section and sign up for a free trial. You can play with up to 20 nodes at our website. So just click the start free trial button and try our product. If you need any consultant or anything like that, you can always reach out to us. We will be more than happy to assist. You have my email as well here. So if you would like to copy it. And another very important thing I wanted to show is that we actually have a section within the EKS-Workshop.com website of AWS about Ocean specifically. So you can always go to this page. So feel free to reach out to that as well. And thank you very much for joining us today. Hope it was useful for you guys, and have a great day.